In this video, we're going to be looking at topic 4A, Introduction to Organic Chemistry, and this is part of the IAS chemistry course from Edexcel. So we're going to be looking at the differences between hazards and risks, and why we need to carry out risk assessments when we're using specific organic compounds, how we can reduce these risks, and how we can carry out reactions safely. We'll also be looking at homologous series and functional groups, as well as how to name organic compounds using IUPAC nomenclature, how to classify reactions, and looking at different types of bond breaking, as well as the terms free radical and electrophile. Now, what you will find is that a lot of this topic you will have covered at IGCSE, so some of this should be revision for you. There will be a couple of things that are brand new, and we'll point them out as we go. So hydrocarbon is a substance that is made of hydrogen and carbon only. Now, you will have met this in GCSE, and this is a typical 2-mark question where you had to specify the hydrogen and carbon, and it was only made up of these. And that's what we're going to focus on in this topic. We're going to be looking at hydrocarbons, and in topic 5, we're going to be looking specifically at alkenes, as opposed to the alkanes that we'll cover in 4B. Now, we can classify hydrocarbons as saturated or unsaturated, and this is all to do with the presence of a double bond. You can also, of course, have triple bonds, but we don't go into that in international A-level. So our saturated hydrocarbons have just single bonds, and our unsaturated will contain a double, or as we said, they can contain a triple bond. So there are different families of hydrocarbons that you need to be aware of. You will have met alkanes and alkenes last year, and you will have briefly been made aware of cycloalkanes, and there's also cycloalkenes. And for each of these, we can name them differently, we can have their own structures, and we all have can give them general formulas. So we have alkanes with the general formula CnH2n plus 2. We have alkenes with CnH2n. Cycloalkanes also have CnH2n, but you can see that they have this ring structure as opposed to the double bond. And cycloalkenes have the ring structure and the double bond, so they have the general formula CnH2n minus 2. Now, these two are the ones that we're going to focus on most. If you're asked about cycloalkanes and cycloalkenes, similar to GCSE, they tend to be more problem-solving style questions. So when we're looking at different types of formula, there are 5 different types that you have to be able to do. You've met 4 of these in GCSE, so only 1 should be new. We have empirical formula, where we have our simplest whole number ratio. We have molecular formula, where it's the actual numbers of carbons and hydrogens. We have skeletal formula, where it just shows the bonds between the carbon atoms. Structural shows how the molecules are joined together, so in small chunks. And displayed shows every single atom and every single bond. So if we look at an example, we can have butane and chloroethane. So for displayed, we can show every single carbon and every single hydrogen with all the bonds. When we have skeletal structure, we just draw lines, and what we are saying here is that each of the points is a carbon atom. And we also make the assumption that that carbon atom has a specific number of hydrogens attached. If it is on the end, then it would be a CH3, and if it's here and this in the middle, it would be a CH2. So it's just a quicker way for us to show structures, and you'll see these skeletal formulas being used more and more when we have more complex structures. We can have structural, where it breaks it down into different chunks. So we have a CH3, a CH2, a CH2, and a CH3. Molecular, C4H10, so I have 4 carbons and 10 hydrogens. And empirical, well, that can be broken down into a simpler whole number ratio of 2 carbons for every 5 hydrogens. And chloroethane is very similar. This time, though, we have a chlorine atom on the carbon. So when we're drawing out our skeletal formula, again, this is a carbon, this is a carbon, and we assume that the hydrogens are already there, but we have to physically show that the chlorine, so this is assumed to be CH2, and this one is assumed to be a CH3. And again, our structural formula, our molecular formula, and our empirical formula to show the different types of ways that we can put this together. Again, you met these two definitions back in GCSE. So we had a functional group, which is an atom or a group of atoms in a molecule that give a compound its distinctive and predictable properties. Because remember, all of these groups of atoms or groups of compounds that we're meeting, they all have very similar chemical properties. So examples of a functional group would be an OH, which can be found in an alcohol, a COOH, which can be found in a carboxylic acid, or a carbon-to-carbon double bond, which can be found in an alkene. Now, if you did triple last year, you would have met alcohols and carboxylic acids. You will also meet them again in topics 10, 15, and topic 20. But for now, we're just going to be focusing on hydrocarbons, and we will come back to talking about alkenes. We also met the term homologous series. So a homologous series is a family of compounds that all have the same functional group. So they all have an OH group or a carbon-to-carbon double bond and so on. And they differ by CH2 from the next member, meaning the chain length is increasing by 1 carbon and 2 hydrogens each time. They're also going to show similar chemical properties and physical properties that show a graduation or a trend. And we will talk more about them when we look at the alkanes and alkenes in more depth. And they also share a general formula. So for example, CnH2n plus 2. So all alkenes will follow the same general formula. And we can see some more examples of general formulas. So we have the alkenes, the alkanes, halogenalkenes that we will discuss in topic 10. So when we have an alkene with a halogen attached, and also alcohols, again, we'll discuss in topic 10. Now, because we have a homologous series, we said that they're all going to react in very similar ways. So for example, all alkanes will undergo complete combustion to make carbon dioxide and water because they are all hydrocarbons. All alcohols are going to show a trend in boiling temperatures, so that would be looking at our physical properties. And what we see is that the temperatures are increasing as the molar mass increases. So this is an example of the properties of homologous series. We're looking at not only the formulas, but also the chemical and the physical properties. Moving on to nomenclature and how we name compounds. Again, you met this back in IGCSE, and I suggest that you practice this to make sure you are completely confident with it. But in order to name these compounds, we use rules for prefixes, suffixes, and locants. Now, you probably didn't use these terms in GCSE, but you actually do already know what they are. So when we're looking at the part of the name, we're looking first of all at the number of carbons. So for example, meth meaning 1, eth meaning 2, prop meaning 3, and so on. The prefixes are something that goes in front. So for example, if you have a bromine, you would use the prefix of bromo. If it was chlorine, you would have chloro, and so on. And suffixes is something that goes at the end. So if you have a hydroxyl group, you change the ending to -ol. For example, ethanol. Or if it's a carboxyl group, it would be ethanoic acid. And again, we'll look more at these nomenclature examples when we do alcohols and carboxylic acids in topic 10. We can also have multiplying prefixes, so to tell me how many side chains I have, so di being 2, tri being 3, and so on. And locants is the position of the chain. So I have a side chain on carbon number 2, so I would use the number 2 at the start. We use this systematic naming method that was determined by the International Union of Pure and Applied Chemistry, or IUPAC, and we follow the same set of rules every time, and these are followed worldwide so that every compound has the same name worldwide and we're not getting confused when we're looking at different languages. So in terms of nomenclature, how we do this is we first identify the longest continuous chain of carbons. We then number the carbons so that the branch or the functional group is on the lowest possible number. We identify the position, the number and the type of branches, and then we name the structures starting with the branches and ending with the length of the alkane chain. So if we look at a few examples, we've got propane, we have methyl propane where we have a methyl group on one of the carbons. I have 3-methyl pentane telling me I have a 5-carbon chain with a side chain on carbon number 3. I could then have 2-methyl pentane where my side chain is on carbon number 2. I could have 2,3-dimethyl butane, so I have a 4-carbon chain with 2 methyl groups on carbons 2 and 3, or 3-ethyl 2-methyl pentane, giving me a 5-carbon chain with a methyl group on carbon number 2 and an ethyl group on carbon number 3. Now, ethyl groups are not particularly common in naming conventions or when we do examples, but be aware that we can have them coming up in an exam. This illustrates a rule about the prefixes being in alphabetical order. So we put ethyl before the methyl because E comes before M. We can also look at the nomenclature of alcohols. So if we have ethane as our main structure and then we add the hydroxyl group, then this becomes ethanol. I can have propan 1-ol to tell me that my OH group appears on carbon number 1. I could have 3-methyl butan 2-ol, so I have 4 carbons in my longest chain. On carbon number 2 is my OH group, and on carbon number 3 is my methyl group. Or 3,3-dimethyl butan 1-ol, so a 4-carbon chain for the butanol. The OH group is on carbon number 1, and I have 2 methyl groups on carbon number 3. Again, we will discuss these in topic 10. So let's look at 1 or 2 examples. So the first thing that you should do is you should identify your longest continuous chain. Well, that's going to be my center, and I'm going to number my carbons. There's 1, 2, and 3. So I know that my chain is prop. It is completely saturated. So this is going to be ANE, it's an alkane. And I have a branch, which is a methyl, and it is on carbon number 2. So this is 2-methyl propane. I then look at the second one. My longest continuous chain is the 4 carbons. Now I want to number it so that my carbons are on the lowest, my branch is on the lowest possible number. And if you're not sure the best way to do this, you can number left and right. So if I number 1, 2, 3, and 4, and then 1, 2, 3, and 4, my chain can either be on carbon 2 or carbon 3. So we know that we want the lowest number, so we're going to use the top set of numbers. So I have butane, which is my chain. I have a methyl group, and it is on carbon number 2. So this is 2-methyl butane. And there's our answers. 2 more. This one is a little bit more tricky. We're looking for the longest continuous chain, and a trap to fall into would be to say it is 1, 2, 3, 4, 5. But actually, my longest continuous chain doesn't go there. It actually goes up 5 and 6. They may purposely give you a slightly more difficult example in order to try and catch you out, but you need to count until you get from one end to the other without stopping in terms of carbons, and you have the highest possible number. So this is going to be a hexane, and my carbon is going to be on, well, I could have it as 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So my chain will either be on carbon 3 or carbon 4, but we want to have it as the lowest number. So I'm going to get rid of the first set. And my chain is a methyl group on carbon number 3. So that's 3-methyl hexane. And lastly, My longest continuous chain is going to be propane, because I have my 3 carbons in a row, and I have 2 methyl groups this time, so I write methyl and I put a di in front of it, and then I have to put where they're located, and it is on carbon 2 and carbon 2. So this is 2,2-dimethyl propane. And there you can see the answers. Now, we also met isomers back in IGCSE. So isomers are compounds that have the same molecular formula, but different structural formulas. So for example, if we have the molecular formula C5H12, where I have 5 carbons and 12 hydrogens, I can have different structures of ways of putting these together. So I could have all 5 carbons in a row, giving me pentane. I could have 4 carbons in a row with 1 chain, giving me 2-methylbutane, or I could have 3 carbons in a row with 2 chains, giving me 2,2-dimethyl. That should be propane. Apologies for the mistake there. Now, there are 2 different types of structural isomerism, and that is chain isomerism, so having different lengths of carbon chains, for example, having 5 carbons in a row or having 4 carbons in a row. Or we can have what's known as position isomerism, where we can change the position of the functional group. So here, the OH group is on carbon number 1, whereas here, it's on carbon number 2. Those are examples of positional isomerism. Now, if you have a double bond, you can also have positional isomerism with the movement of the double bond throughout the chain, but we can also get chain isomerism where we can have different lengths of carbons. For example, we can have but-1-ene versus but-2-ene, where we've changed the position of the double bond, but we can also have 2-methyl-prop-1-ene, where we've changed the chain length from 4 to 3. These are all isomers of the same molecule. So these are all C4H8, and we will cover them more when we look at topic 5A, which is the alkenes. Now, you should be able to draw structural isomers for all of the alkanes and the cycloalkanes up to 6 carbons. So when you have a cycloalkane, you should be thinking about a ring structure. So starting from cyclopropane, where we have 3 carbons in a ring, going up to cyclohexane, where we have 6 carbons in a ring. And we'll practice these more when we look at the alkanes later on. But it's good practice to figure out the different types of isomers and practice naming and drawing the isomers for different formulas. You can ask your teacher to provide you with some questions, or you can simply look up some questions on the internet. Now, moving on to different types of reaction for organic substances. These are some that we're going to come across all the way through the organic compound portion of the A level. So we're looking at addition, where we get 2 reactants combining to make 1 product. Substitution, where 2 reactants combine to make 2 products. Oxidation, where a substance either loses hydrogen or gains oxygen. The opposite of that being reduction, so the gain of hydrogen or losing oxygen, and polymerization, where we get monomers combining to make polymers. You have met these 3 before, and you will have met oxidation and reduction, but you will have met them in terms of inorganic chemistry, talking about electrons. When we're talking about organic chemistry, we're looking at a slightly different explanation. We're looking at the loss or gain of oxygen, and we'll cover these later in topic 10. So here's just some examples. If we have an alkene and we add hydrogen to make an alkane, that's addition reactions. If we have a substitution to swap out this OH for a Br, and then we make an alcohol and a bromide. We can have an oxidation of an alcohol to make a substance known as an aldehyde. And again, we'll learn more about that in topic 10. We can have reduction to go from the aldehyde back to the alcohol, or we can have polymerization, so going from an alkene to a polymer. And we will cover all of these different types of reactions as we go through this organic section. Two other key terms that we're going to meet in topics 4 and 5 is looking at bond breaking. And there are two different types of bond breaking, and we call these homolytic fission and heterolytic fission. So homolytic fission is when our shared pair of electrons in the covalent bond are divided equally. So each atom takes one electron and we form something known as a free radical. And this just means that we have an unpaired electron. And we will talk more about them in topic 4b. We can then have heterolytic fission, where the shared pair of electrons are kept by one of the atoms, so the one with the higher electronegativity. And this then forms a positive or a negative ion. And we will look at these in topic 5a. So homolytic fission, the electrons are shared equally. Heterolytic fission, they are kept by one of the atoms. We are also going to be introduced to something known as an electrophile. Now, if something has the word phile in it, that means to like. And if it has electro, this means electrons or a negative charge. So electrophiles are substances that are attracted to an area of high electron density. So this is going to be attracted to areas of where there is a lot of negative charge. So electrophiles are positive ions, and they are attracted to negative charge. And that typically is going to be when we have a dipole and we have a delta negative. So we have that difference in electronegativity pulling the electrons closer to make this slightly negative. We will cover electrophiles in reaction mechanisms in topic 5a and 5b when we're looking at alkenes. Now, it's important that we understand the difference between hazards and risks. A hazard is something that can cause harm to a user, and a risk is the chance of that hazard causing harm. Most people will use these interchangeably, but within science, these do mean two different things. So do make sure that you can distinguish between them. And you'll have seen that all laboratory substances are labelled with hazard symbols to identify the actual hazard. So they'll have a symbol like shown in the table where we can have a health hazard. So it could be something that is corrosive or can be an irritant and cause skin rash or eye damage. We can have something that is corrosive that could cause a burn. So you may see this on something like an acid. We can have flammable that you may see on, for example, an alcohol. So it will catch fire very easily if it comes into contact with a flame. Or something that is acutely toxic. So maybe like cyanide, that in even very small quantities can be extremely life-threatening. So when we have these organic substances, they tend to all carry their own risk and their specific hazards. So what we have to do is we have to typically carry out a risk assessment when we're using these. And a risk assessment is basically what it sounds like. It's identifying the hazards that are in a procedure and how we can reduce the risk of them happening or the risk of them causing harm. So we have to look at what control measures we use. So, for example, we might be thinking about, in a risk assessment, the age and the experience of the person using the substances. So if you've got someone that is very experienced, they're unlikely to make the same mistakes as someone who has never met this particular chemical before, or they're just brand new to using it. For example, a year 13 student will be more comfortable and better at using acids because they've been using it for years, as opposed to a year 7 who could be meeting it for the first time. We'll also be looking at what amount it would be used, how much you're going to be heating it, or if you're heating it, and what ventilation is possibly needed. So are there toxic fumes? Are you going to need a fume cupboard? Can it just be enough just to open the window? So all of these type guidelines are going to be typically found in a risk assessment, and it's things that you will always go over. Specific control measures will be the basic things that you'll know already, so eye protection, goggles, wearing gloves, and using lab coats, but also about simple things, keeping the substance away from heat if it's flammable, making sure to keep the cap on a bottle if something is corrosive because we don't want it spilling, or if something does spill, how do we deal with the spillage? That also has to be put in a risk assessment. A lot of times it's not as easy as to just simply wipe it up and throw it away. Sometimes some things need to be neutralised or mixed with another chemical before they can be disposed. So this is an example of a risk assessment or hazards, risks and control measures, and you may find some of this even in things within your home. So we've got oven cleaner, and we're saying that this is a corrosive substance. So hazard statements would say it can cause severe skin burns and eye damage. So we want to wear protective gloves, protective clothing, eye and face protection. If we get it on our hands, we need to wash them thoroughly. It also tells you what to do if you do come into contact with it. So what to do if it's swallowed, it gets in your eye or on your skin, and also how to dispose of it. So this is a summary of the risk assessment that has been carried out on this particular oven cleaner that is then displayed on the bottle so that someone who is new to using it will know how to deal with it. So let's finish off by looking at a past paper question. So we've got the naming of an organic compound, and this is a multiple choice. You tend to find that these tend to be multiple choice, and we want to be thinking about, first of all, the longest continuous chain. So we know that we're going to be looking probably at this center part. So we're going to have 1, 2, 3, 4 for our substance. So we know we're going to be having a butane as our longest continuous chain. So we can automatically get rid of A and get rid of B. So now we need to determine what the chains are. So we have a methyl group. Remember, we don't have to actually show it, but you could always draw it in if you're not sure. We have a methyl group on carbon number 3, and we have a chlorine on carbon number 2. So if we have chloro and methyl, we need to think about what one is going to come first. Well, the one that's going to come first is the chloro, and we can see that in our names here. And we have one methyl group. Well, if we look at D, we can see it says dimethyl, so we can automatically get rid of that, leaving us with the answer of C. So this is 2-chloro, 3-methyl butane. And there you can see our answer is C, and it gives us some explanation as to why the others are not correct. And lastly, from the June 2017 paper, what's the systematic name for this hydrocarbon? Well, this is very, very tough because we want to be thinking about the longest chain. And again, the trap that people will fall into is to simply go between the left-hand side here to the right-hand side here and say that that's 5. But we need to take into account the fact that we have this chain here. And actually, our longest chain is 6. We've got 1, 2, 3, 4, 5, 6 carbons. So we can immediately get rid of A and B. We know that it is going to be hexane. We also can see that we have got 3 branches. We have one here, a second one here, and a third one here. And we can see that in our substance that it's trimethylhexane. Now we need to figure out, are these on carbon number 3 or carbon number 5? 3 and 5 are carbon numbers 2 and 4. So I'm going to number both ways. Just to double check. Now we know that we want the lowest possible number, so hopefully you're automatically being drawn to D, but let's just have a look. We can have the carbons on 3 or 4 and 5 and 2. Well, the 2 is the lowest possible number, so we're going to get rid of the numbers on the top hand side. So we have 2 methyls on carbon number 2 and 1 methyl on carbon number 4, giving us an answer of D. And there is the mark scheme. Now that's everything for topic 4A, Introduction to Organic Chemistry. You will touch on all of this all the way through your organic learning, and we'll be looking at this in more detail specifically in topics 4B and 5A when we're looking at the alkanes and alkenes. I would suggest that you do get some practice on naming and drawing hydrocarbons, remembering what you did in GCSE. So you can either check in the textbook, have a look back at GCSE questions, or ask your teacher. Of course, if you have any questions, you can leave a comment below, and we hope to see you back soon.